Today I'm going to take a look at the power consumption of a nRF24L01 transceiver. I've been looking at these a little bit, and the 24L01 is a neat little data radio operating in the 2.4 gigahertz range. They can operate at fairly low power. They can be great for battery-powered applications due to their low sleep current, and has a lot of nice little features built into them. They can be asleep, wake up, transmit, receive, and go back to sleep very quickly. How quickly? Well, I'm going to look into that too. My intent is to create a small sensor node with a microcontroller which will periodically wake up, check inputs, transmit, go back to sleep. I could use any of a variety of cheap transceivers, but then I would have to implement the protocol and perform data validation. I also might have to transmit several times to ensure the signal was received. Some of these gadgets are extremely cheap. Like these, I think are, last time I bought one was maybe a few years ago. They were maybe 80 cents each, a couple of models, and so there's a lot of options there, but they suffer from range and all kinds of problems. You could even go with something more like an XB. This is a pretty expensive device, often running $20 to $40 depending on the model, but the NRF unit is this one. I think these are running about 80 cents to $2 depending on where you're buying them. The higher power, longer range model with the external antenna and the power amplifier probably are running around $4 to $6, so very affordable. The nRF also has a handy auto-acknowledge feature in which my sensor node could send out the data, and the central receiver would instantly acknowledge that transmission, letting the sensor know that the signal got through and it doesn't need to try again. That can also simplify testing the sensors when I install them, as I could just press a button over on my sensor node and have it turn on a nice little green LED or something, indicating that the receiver has acknowledged getting the signal. So I don't have to try to place the sensor, trigger it, try to make sure that I saw that the light came on the receiver, etc. So that'll be a handy thing to do. But let's see what all of this kind of capability costs in the way of power. So we'll have a central, we'll call it a receiver unit, that picks up the signals from the nodes and does something with them. That'll be just simple, it's connected to the PC with a USB cable to an Arduino. Then we'll put a little LED on there that will blink every time we receive a signal. We'll toggle the LED on and off. And then that is connected to the first nRF24L01 via SPI. And the Arduino's 3.3 volt output will be used to run that. Next we have the node, and again, for now we'll use an Arduino Pro Mini. We'll power it from USB. What I'm mostly interested in right now is the power consumption of the radio unit itself, because there are a variety of 18 mega chips that I could be using here, or I could replace this with a PIC, or who knows what, to get better power consumption. And so to run that, we'll run the Arduino off of one power supply, the nRF24L01 off of a separate lab supply that we can then measure, see what the output is, and we've got a little switch as our signal sensor. And all we had to do was couple the grounds here. We are not connecting a power line from the Arduino to the radio. So here we have the receivers and an LED on it which will toggle on and off each time it receives a valid packet. It's powered by just simple USB power. Here we have our sensor node. It's powered by USB as well. The Arduino is, except that what we've done is disconnect the power from the board for the transceiver here, and we're going to power that off our bench power supply. And each time we move the switch, this will transmit a data packet. Well, we're showing 2 milliamps, and I'm pretty sure this board takes more than 10 in order to transmit a packet. And each time we send, we're not seeing any change in the consumption, so maybe we need to try something else. And now it's gone down. One of the things that might do next is insert a more sensitive meter in here, but let's do one better. Instead of using the old Rigol PSU and DMM for this test, we'll use the Keithley 2280S power supply. With a built-in 6.5 digit meter and acquisition times as low as 33 microseconds, this should be able to pick up any short current pulses when the radio powers up. In my previous video using the 2280S, I pointed out I/O terminals on the back of the unit. We'll need them for this test as we want to trigger a series of measurements as the radio powers up and then until it goes back to sleep. Here's our setup. We're going to power the Arduino Pro Mini, again from USB power, as all we want to measure is the power being consumed by the radio. The radio is connected to the Arduino through SPI. We also have a ground connection over to provide common ground between the two. The Keithley is going to provide the power to the radio, and the Arduino is going to also generate a trigger signal for the 2280 in order to make sure that the meter specifically triggers right before the radio powers up so that we can catch both low power mode, then powered up, and then powered off in the samples. That's what I want to try and capture. Now, normally to perform this test, you'd need to include a high-speed DMM to measure the power, but I think with the 2280S I can get away without that. Following the Keithley application note 3277, we need to use I/O pins 1 trigger in, 9 ground, and I believe that pin 7, 5 volts, which is 5 volt isolated power provided by the meter, and we can use that as a pull-up. Now, since the 2280S triggers on a falling 5 volt input and our radio is enabled on a 3.3 volt high signal, I've inserted this same simple circuit to trigger the 2280S. So when the Arduino triggers the radio, that will pull the trigger to ground and start the measurements. Now there's quite a bit of gear on the back of this bench, and to get to the back of that stuff is a real hassle. So to do that I have to roll the bench out from the wall, and of course first I have to disconnect and roll up the anti-static mat, then unlock the wheels and slide it out. But to do that I have to also swing this beast of an equipment rack out of the way, and that's fairly heavy, but it rolls pretty well. It has all the monitors, servers, other gear, parts, etc. And so just getting to the back of the bench is kind of a pain. So my thought was I might, instead of just one-off hooking up to the trigger pins on the back of that power supply, I might build a breakout box and run that around to the front. With the large equipment rack rolled back, there's room to swing out the main bench and get around to the back of it. Here's the power supply and the I/O connector on the upper right corner. The breakout box is assembled from a scrap of ribbon cable and a DB9 connector, and a few 5mm terminals on a small project box I had laying around from a remote control project. Now to push the bench back. We now have the circuit all hooked up with the Arduino connected to the trigger circuit and the trigger circuit connected to the inputs on the back of the unit through our breakout and then off to the meter. Now what we need to do is follow the rest of the instructions in application note 3277 from Keithley to configure the power supply to trigger. First off, we need to change the measurement to only measure current, because we don't really care about the voltage. Then we need to go into the menu system and go into turn off the filtering. So we'll filter state to off. Then we change the NPLC. That's should be under measurement. There we go. Let's set the let's go ahead and change the range. Let's set that to 100 milliamps. That should be more than enough for our pick up our radio. We need to turn auto 0 to off because that's going to slow it down. And then we need to set our NPLC, and the easiest way to get that to the max is to go over to the first digit there and just turn it all the way down. That'll put it to 0.002. Alright, then we need to configure the trigger, and again that's another menu option, trigger. In this case we need to change the arming source to be external, and also set some samples, so figure out how many samples we want, and in this case I'll go ahead for, I don't know, 60 samples. And that should take care of it. I want to point out something here. You don't have to do this kind of thing all of the time. You have an option under, let me back that up, under System, Save Recall, on the far right top corner, to save and recall settings, and that's simple enough. You can just go in, you can save a series of these, and it's nice and easy to get yourself back to where you need to be. Let's take a look at the triggering and see how the signals look coming in. So from here we have the Arduino's input trigger pin coming in, hooked up to one probe, the transistor, which is going to pull that signal down, the pull-up resistor here, and the other probe. Here we can clearly see the triggers coming across. So our signal from the radio powers up, the transistor pulls the output, trigger output down from 5 volts. So we've got our 3.3 volt signal here, our inverted 5 volt pulse, and we're triggering every second. Now we're all set up. Let's go into clear out our buffer in case there's any data. Let's go to graph mode. We'll power up the radio. Get a little noise as it powers up. Now each time I toggle it, the LED toggles along with it for every data packet, and we see a nice spike showing up with each triggering of the radio. Now let's zoom in on some of that data. I'm not sure how readable this will be on the screen, but we're showing a minimum on our statistics of 8 microamps and a max of 13.18 milliamps. So when the radio is off or in its sleep state, it is very, very low power mode, really low power. And then we're getting 13 milliamps when it fires up, which was not picked up by the regular bench supply. So let's take a closer look at those numbers. We can look at the raw data sheet, but yeah, there's the raw numbers. It may take a while sometimes to find stuff in this. It's easy enough to export the data. Go into the menu, scroll down to data buffers, export to USB, and we'll call it file A. Works for me. Alright, and here's our data. Oh boy, we've got a lot of numbers here. It's going to be hard to make sense out of that. And for each reading, we have the voltage. Now this is not the voltage that was reading back in. This is the set voltage because we were only measuring current. That's what we had it set to. And here's the date time down to seconds. And then we have fractions of a second. So it goes down to 4 digits or tenths of a millisecond. That'll be, I'm hoping that's good enough for the measurements I need to take. Well, let's see if we can make some sense out of this data and find one of our peaks. Ah, there we go. There's our pulses. They appear right out of the noise. Let's take a look at one at point 21. So data point 21, 13 milliamps and 8 milliamps right here. And that lasted 0.4 milliseconds, 0.4 of a millisecond. That's very short. Let's try another data point. Okay, let's look around 125. And at 125 we can see 13 milliamps. Here's the beginning of a pulse. Alright, so it starts at coming up at 9.5 milliamps, then to 13, and then back down to 6 milliamps as it drops off. And that lasted 1.7 milliseconds. So very short pulse. No wonder the Rigel lab power supply didn't show that. It was just lost in the noise. So this is what a really nice power supply can do. Can graph out those peaks, and I didn't have to use include a DMM in it. All I had to do is switch over to the graphing mode, and there it is. So we've measured the power use of the transceiver and found that it is actually very efficient with very low resting state power and only very short pulses of 13 milliamps when it transmits. If I'm going to make this into a node, though, I need to include some sort of a microcontroller, and I might use the Arduino right here, or I might need to find something more efficient. One of the things about these Arduino boards is they're really not off the shelf designed to be really power efficient for battery operation. Let's look at that schematic. Here's the diagram of our Pro Mini. We have the core chip over here, and on the left we have some additional circuitry for power. Since the Arduino can be powered via USB, it has a voltage regulator here, and then it also has a handy little power LED, which is kind of nice when you're prototyping. But, well, what if we could just power it by VCC, inject 3 volts directly, so that all we were doing is worrying about the power needed for the chip? Because these voltage regulators are notorious for their power waste, and I really don't need an LED. So I have removed both of these components from the board, and now we're down to really just the bare circuit. We have some power and bypass capacitors, and that's really about it, along with a crystal. So in our new configuration mode, we've removed the USB power, and the Arduino is being powered by the Keithley power supply and the radio as well. What we're doing next is to measure the entire power consumption of the radio and the Arduino as it runs, and the Arduino is now programmed to go into a sleep mode and then wake up every second, check its input, and perform some transmissions. A little hard to see some of the data, but we're picking up peaks when it is actually transmitting of up to 15 millivolts or thereabouts, 15 milliamps, and we get a sleep current, again, very low, around 12 microamps. So the Arduino is actually pretty efficient when it's asleep. So maybe this will be a viable node after all, and I won't need to go to a PIC. So this has worked out exactly as I had hoped. We've managed to get a sensor node running with a wireless small transceiver, and managed to get the power consumption down very low. The power supplies worked out great. Although numbers often don't mean much as they scroll across the screen, as soon as we go into graph mode, it all comes to life. We can see what we need to see, and we can capture the data and analyze it in more detail. So that's worked out really well. And like the trigger functions, that's worked. Keithley's application notes helped out, worked exactly just by the way I wanted, just by following the simple instructions there. So same with the trigger setup on the menus. So all in all, very pleased. And we'll be using this power supply some more when I get a boost converter going to run this off batteries.